Chapter 3 Principles of Flight. Introduction. This chapter examines the fundamental physical laws governing the forces acting on an aircraft in flight and what effect these natural laws and forces have on the performance characteristics of aircraft. To control an aircraft, be it an airplane, helicopter, glider, or balloon, the pilot must understand the principles involved and learn to use or counteract these natural forces. Structure of the atmosphere. The atmosphere is an envelope of air that surrounds the earth and rests upon its surface. It is as much a part of the earth as the seas or the land. But air differs from land and water as it is a mixture of gases. It has mass, weight, and indefinite shape. The atmosphere is composed of 78% nitrogen, 21% oxygen, and 1% other gases, such as argon or helium. Some of these elements are heavier than others. The heavier elements, such as oxygen, settle to the surface of the earth, while the lighter elements are lifted up to the region of higher altitude. Most of the atmosphere's oxygen is contained below 35,000 feet altitude. Air, like fluid, is able to flow and change shape when subjected to even minute pressures because it lacks strong molecular cohesion. For example, gas completely fills any container into which it is placed, expanding or contracting to adjust its shapes to the limits of the container. Atmospheric pressure. Although there are various kinds of pressure, pilots are mainly concerned with atmospheric pressure. It is one of the basic factors in weather changes, helps to lift an aircraft, and actuates some of the important flight instruments. These instruments are the altimeter, airspeed indicator, vertical speed indicator, and manifold pressure gauge. Air is very light, but it has mass and is affected by attraction of gravity. Therefore, like any other substance, it has weight, and because of its weight, it has force. Since it is a fluid substance, this force is exerted equally in all directions, and its effect on bodies within the air is called pressure. Under standard conditions at sea level, the air pressure exerted by the weight of the atmosphere is approximately 14.70 pounds per square inch or psi of surface or 1013.25 millibars. Its thickness is limited, therefore the higher the altitude, the less air there is above. For this reason, the weight of the atmosphere at 18,000 feet is one half what it is at sea level. The pressure of the atmosphere varies with time and location. Due to the changing atmospheric pressure, a standard reference was developed. The standard atmosphere at sea level is a surface temperature of 59 degrees Fahrenheit or 15 degrees Celsius and a surface pressure of 29.92 inches of mercury or 1013.25 millibar. The standard temperature lapse rate is one in which the temperature decreases at the rate of approximately 3.5 degrees Fahrenheit or 2 degrees Celsius per 1000 feet up to 36,000 feet, which is approximately minus 65 degrees Fahrenheit or 55 degrees Celsius. Above this point, the temperature is considered constant up to 80,000 feet. A standard pressure lapse rate is one in which the pressure decreases at a rate of approximately 1 inch of mercury per 1000 feet gain of altitude to 10,000 feet. The International Civil Aviation Organization (ICAO) has established this as a worldwide standard, and it is often referred to as International Standard Atmosphere (ISA) or ICAO Standard Atmosphere. Any temperature or pressure that differs from the standard lapse rates is considered non-standard temperature and pressure. Since aircraft performance is compared and evaluated with respect to standard atmosphere, all aircraft instruments are calibrated for the standard atmosphere. In order to account properly for non-standard atmosphere, certain related terms must be defined. Pressure altitude. Pressure altitude is the height above a standard datum plane (SDP), which is a theoretical level where the weight of the atmosphere is 29.92 inches of mercury or 1013.2 millibar as measured by a barometer. An altimeter is essentially a sensitive barometer calibrated to indicate altitude in the standard atmosphere. If the altimeter is set for 29.92 inches of mercury (SDP), the altitude indicated is the pressure altitude. As atmospheric pressure changes, the SDP may be below, at, or above sea level. Pressure altitude is important as a basis of determining airplane performance, as well as for assigning flight levels to airplanes operating at or above 18,000 feet. The pressure altitude can be determined by either of two methods. 1. Setting the barometric scale of the altimeter to 29.92 inches of mercury or 1013.25 hectopascals and reading the indicated altitude, or 2. By applying a correction factor to the indicated altitude according to the reported altimeter setting. Density altitude. SDP, or standard data plane, is a theoretical pressure altitude, but aircraft operate in non-standard atmosphere, and the term density altitude is used for correlating aerodynamic performance in the non-standard atmosphere. Density altitude is the vertical distance above sea level in the standard atmosphere at which a given density is to be found. The density of air has significant effects on the aircraft's performance because as air becomes less dense, it reduces the power because engines take in less air, thrust because a propeller is less efficient in thin air, and lift because the thin air exerts less force on the airfoils. Density altitude is pressure altitude corrected for non-standard temperature. As the density of the air increases, that is lower density altitude, an aircraft performance increases, and conversely as the air density decreases, that is higher density altitude, the aircraft performance decreases. A decrease in air density means a high density altitude. An increase in air density means a lower density altitude. Density altitude is used in calculating aircraft performance because under standard atmospheric conditions, air at each level in the atmosphere not only has a specific density, its pressure altitude and density altitude identify the same level. The computation of density altitude involves consideration of pressure, that is pressure altitude, and temperature. Since aircraft performance data at any level is based upon air density under standard day conditions, such performance data apply to air density levels that may not be identical with altimeter indications. Under conditions higher or lower than standard, these levels cannot be determined directly from the altimeter. Density altitude is determined by first finding pressure altitude and then correcting this altitude for non-standard temperature variations. Since density varies directly with pressure and inversely with temperature, a given pressure altitude may exist for a wide range of temperatures by allowing the density to vary. However, a known density occurs for any one temperature and pressure altitude. The density of the air has a pronounced effect on aircraft and engine performance. Regardless of the actual altitude at which the aircraft is operating, it will perform as though it were operating at an altitude equal to its existing density altitude. Air density is affected by changes in altitude, temperature, and humidity. High density altitude refers to thin air, while low density altitude refers to dense air. The conditions that result in a high density altitude are high elevations, low atmospheric pressures, high temperatures, high humidity, or some combination of these factors. Lower elevations, high atmospheric pressure, low temperatures, and low humidity are more indicative of low density altitude. Effect of pressure on density. Since air is a gas, it can be compressed or expanded. When air is compressed, a greater amount of air can occupy a given volume. Conversely, when pressure on a given volume of air is decreased, the air expands and occupies a greater space. At a lower pressure, the original column of air contains a smaller mass of air. The density is decreased because density is directly proportional to pressure. If the pressure is doubled, the density is doubled. If the pressure is lowered, the density is lowered. This statement is true only at a constant temperature. Effect of temperature on density. Increasing the temperature of a substance decreases its density. Conversely, decreasing the temperature increases the density. Thus, the density of air varies inversely with temperature. This statement is true only at a constant pressure. In the atmosphere, both temperature and pressure decrease with altitude and have conflicting effects upon density. However, the fairly rapid drop in pressure as altitude is increased usually has the dominating effect. Hence, pilots can expect the density to decrease with altitude. Effect of humidity or moisture on density. The preceding paragraphs refer to air that is perfectly dry. In reality, it is never completely dry. The small amount of water vapor suspended in the atmosphere may be almost negligible under certain conditions, but in other conditions, humidity may become an important factor in the performance of an aircraft. Water vapor is lighter than air. Consequently, moist air is lighter than dry air. Therefore, as water content of the air increases, the air becomes less dense, increasing density altitude and decreasing performance. It is lightest or least dense when in a given set of conditions it contains the maximum amount of water vapor. Humidity, also called relative humidity, refers to the amount of water vapor contained in the atmosphere and is expressed as a percentage of the maximum amount of water vapor the air can hold. This amount varies with temperature. Warm air holds more water vapor, while colder air holds less. Perfectly dry air that contains no water vapor has a relative humidity of 0%, while saturated air, which cannot hold any more water vapor, has a relative humidity of 100%. Humidity alone is usually not considered an important factor in calculating the density, altitude, and aircraft performance, but it does contribute. As temperature increases, the air can hold greater amounts of water vapor. When comparing two separate air masses, the first warm and moist, both qualifies tending to lighten the air, and the second cold and dry, both qualities making it heavier. The first must be less dense than the second. Pressure, temperature, and humidity have a great influence on aircraft performance because of their effect upon density. There are no rules of thumb that can be easily conveyed, but the effect of humidity can be determined using online formulas. In the first case, the pressure is needed at the altitude for which the density altitude is being sought. Using the figure, select the barometric pressure closest to the associated altitude. As an example, the pressure at 8,000 feet is 22.22 inches of mercury. Using the National Oceanic and Atmospheric Administration (NOAA) website for density altitude, enter the 22.22 for 8,000 feet in the station pressure window. Entering a temperature of 80 degrees Fahrenheit and a dew point of 75 degrees Fahrenheit, the result is a density altitude of 11,564 feet. With no humidity, the density altitude would almost be 500 feet lower. In any case, the effects of humidity on density altitude include a decrease in overall performance in high humidity conditions. Theories in the production of lift. Newton's basic laws of motion. The formulation of lift has historically been the adaptation over the past few centuries of basic physical laws. These laws, although seemingly applicable to all aspects of lift, do not answer how lift is formulated. In fact, one must consider the many airfoils that are symmetrical yet produce significant lift. The fundamental physical laws governing the forces acting upon an aircraft in flight were adopted from postulated theories developed before any human successfully flew an aircraft. The use of these physical laws grew out of the scientific revolution which began in Europe in the 1600s. Driven by the belief the universe operated in a predictable manner open to human understanding, many philosophers, mathematicians, natural scientists, and inventors spent their lives unlocking the secrets of the universe. One of the best known was Sir Isaac Newton, who not only formulated the law of universal gravitation but also described the three basic laws of motion. Newton's first law: every object persists in its state of rest or uniform motion in a straight line unless it is compelled to change the state by the forces impressed on it. This means that nothing starts or stops moving until some outside force causes it to do so. An aircraft at rest on the ramp remains at rest unless a force strong enough to overcome its inertia is applied. Once it is moving, its inertia keeps it moving, subject to the various other forces acting on it. These forces may add to its motion, slow it down, or change its direction. Newton's second law: force is equal to the change in momentum per change in time. For a constant mass, force equals mass times acceleration. When a body is acted upon by a constant force, its resultant acceleration is inversely proportional to the mass of the body and is directly proportional to the applied force. This takes into account the factors involved in overcoming Newton's first law. It covers both changes in direction and speed, including starting up from rest, positive acceleration, and coming to stop, negative acceleration or deceleration. Newton's third law: for every action, there is an equal and opposite reaction. In an airplane, the propeller moves and pushes back the air. Consequently, the air pushes the propeller and thus the airplane in the opposite direction, forward. In a jet airplane, the engine pushes a blast of hot gases backward. The force of equal and opposite reaction pushes against the engine and forces the airplane forward. Magnus effect. In 1852, the German physicist and chemist Heinrich Gustav Magnus (1802–1870) made experimental studies of aerodynamic forces on spinning spheres and cylinders. The effect had already been mentioned by Newton in 1672, apparently in regard to spheres or tennis balls. These experiments led to the discovery of the Magnus effect, which helps explain the theory of lift. Flow of air against a non-rotating cylinder. If air flows against a cylinder that is not rotating, the flow of air above and below the cylinder is identical and the forces are the same. Rotating cylinder in a motionless fluid. In the figure, the cylinder is rotated clockwise and observed from the side while immersed in a fluid. The rotation of the cylinder affects the fluid surrounding the cylinder. The flow around the rotating cylinder differs from the flow around a stationary cylinder due to resistance caused by two factors: viscosity and friction. Viscosity. Viscosity is the property of a fluid or semi-fluid that causes it to resist flowing. This resistance to flow is measurable due to the molecular tendency of fluids to adhere to each other to some extent. High viscosity fluids resist flow, low viscosity fluids flow easily. Similar amounts of oil and water poured down two identical ramps demonstrate the difference in viscosity. The water seems to flow freely while the oil flows much more slowly. You can visit the different types of viscosity at Cornell University website. Since molecular resistance to motion underlies viscosity, grease is very viscous because its molecules resist flow. Hot lava is another example of viscous fluid. All fluids are viscous and have a resistance to flow, whether this resistance is observed or not. Air is an example of fluid whose viscosity cannot be observed. Since air has viscosity properties, it will resist flow to some extent. In the case of the rotating cylinder within an immersed fluid, oil, water, or air, the fluid, no matter what it is, resists flowing over the cylinder's surface. Friction. Friction is the second factor at work when a fluid flows around a rotating cylinder. Friction is the resistance one surface or object encounters when moving over another and exists between a fluid and the surface over which it flows. If identical fluids are poured down the ramp, they flow in the same manner and at the same speed. If one ramp's surface is coated with small pebbles, the flow down the two ramps differs significantly. The rough surface ramp impedes the flow of the fluid due to resistance from the surface, that is friction. It is important to remember that all surfaces, no matter how smooth they appear, are not smooth and impede the flow of a fluid. Both the surface of the wing and the rotating cylinder have a certain roughness, although at a microscopic level, causing resistance for a fluid to flow. This reduction in velocity of the airflow about a surface is caused by skin friction or drag. When passing over a surface, molecules actually adhere, that is, stick or cling to the surface, illustrated by the rotating cylinder in a fluid that is not moving. Thus, 1. In the case of rotating cylinder, air particles near the surface that resist motion have a relative velocity near zero. The roughness of the surface impedes their motion. 2. Due to the viscosity of the fluid, the molecules on the surface entrain or pull the surrounding flow above it in the direction of the rotation due to the adhesion of the fluid to itself. There is also a difference in flow around the rotating cylinder and in flow around a non-rotating cylinder. The molecules at the surface of a rotating cylinder are not in motion relative to the cylinder. They are moving clockwise with the cylinder. Due to viscosity, these molecules entrain others above them, resulting in an increase in the fluid flow in the clockwise direction. Substituting air for other fluids results in a higher velocity of air movement above the cylinder simply because more molecules are moving in a clockwise direction. A rotating cylinder in a moving fluid. When the cylinder rotates in a fluid that is also moving, the result is a higher circulatory flow in the direction of the rotating cylinder. By adding fluid motion, the magnitude of the flow increases. The highest differences of velocities are 90 degrees from the relative motion between the cylinder and the airflow. Additionally, as shown in the figure, at point A, a stagnation point exists where the airstream impacts or impinges on the front of the airfoil surface and splits. Some air goes over and some under. Another stagnation point exists at B, where the two air streams rejoin and resume at identical velocities. When viewed from the side, an upwash is created ahead of the airfoil and a downwash at the rear end. In case of the figure, the highest velocity is at the top of the airfoil with the lowest velocity at the bottom. Because these velocities are associated with an object, in this case an airfoil, they are called local velocities as they do not exist outside the lift producing system, in this case an airfoil. This concept can be readily applied to a wing and other lifting surface. But because there is a difference of velocity above and below the wing, the result is a higher pressure at the bottom of the wing and a lower pressure on the top of the wing. In these figures, A illustrates uniform circulation, B illustrates the increased airflow over the top of a rotating cylinder. The airflow speed is further increased when the rotating cylinder is in a moving stream of air. C. The air molecules near the surface of an object are slowed and almost stationary. D is an example of a typical aircraft grade aluminium used in aircraft construction to include wings and leading edges of wings as shown in E. When magnified at 1500x, polished aluminium is visibly rough. This demonstrates why airflow is affected by molecular irregularities of the surface. Air circulation around an airfoil occurs when the front stagnation point is below the leading edge and the aft stagnation point is beyond the trailing edge. This low pressure area produces an upward force known as Magnus effect, the physical phenomenon whereby an object's rotation affects its path through a fluid to include air. To early aerodynamicists, Martin and Nicolai eventually measured and calculated the forces for the lift equation on a rotating cylinder. To summarize the Magnus effect, an airfoil with a positive angle of attack develops air circulation above the upper surface of the wing. Its sharp trailing edge forces the rear stagnation point to be aft of the trailing edge, while the front stagnation point falls below the leading edge. Bernoulli's principle of differential pressure. A half-century after Newton formulated his laws, Daniel Bernoulli, a Swiss mathematician, explained how the pressure of a moving fluid, that is liquid or gas, varies with its speed of motion. Bernoulli's principle states that as the velocity of a moving fluid, liquid or gas increases, the pressure within the fluid decreases. This principle explains what happens to air passing over the curved top of the airplane wing. A practical application of Bernoulli's principle is the Venturi tube. The Venturi tube has an air inlet that narrows to a throat or constricted point and an outlet section that increases in diameter toward the rear. The diameter of the outlet is the same as that of the inlet. At the throat, the airflow speeds up and the pressure decreases. At the outlet, the airflow slows and the pressure increases. Since air is recognized as a body and it has been accepted that it must follow the above laws, one can begin to see how and why an airplane wing develops lift. As the wing moves through the air, the flow of air across the curved top surface increases in velocity, creating a low pressure area. Although Newton, Magnus, Bernoulli, and hundreds of other early scientists who studied the physical laws of the universe did not have the sophisticated laboratories available today, they provided a great insight to the contemporary viewpoint of how lift is created. Airfoil design. An airfoil is a structure designed to obtain reaction upon its surface from the air through which it moves or that moves past such a structure. Air acts in various ways when submitted to different pressures and velocities, but this discussion is confined to the parts of an aircraft that a pilot is most concerned with in the flight, namely the airfoils designed to produce lift. By looking at a typical airfoil profile, such as the cross-section of a wing, one can see obvious characteristics of the design. Notice that there is a difference in the curvatures, that is called cambers, of the upper and lower surfaces of the airfoil. The camber of the upper surface is more pronounced than that of the lower surface, which is usually somewhat flat. Note, the two extremities of the airfoil profile also differ in appearance. The end which faces forward in the flight is called the leading edge and is rounded. The other end, the trailing edge, is quite narrow and tapered. A reference line often used in discussing the airfoil is the chord line, a straight line drawn through the profile connecting the extremities of the leading and trailing edges. The distance from this chord line to the upper and lower surfaces of the wing denotes the magnitude of the upper and lower camber at any point. Another reference line drawn from the leading edge to the trailing edge is the mean camber line. This mean line is equidistant at all points from the upper and lower surfaces. An airfoil is constructed in such a way that its shape takes advantage of the air's response to certain physical laws. This develops two actions from the air mass: a positive pressure lifting action from the air mass below the wing, and a negative pressure lifting action from the lowered pressure above the wing. As the air stream strikes relatively flat lower surface of the wing or rotor blade when inclined at a small angle towards direction of motion, the air is forced to rebound downward, causing an upward reaction in positive lift. At the same time, the air stream striking the upper curved section of the leading edge is deflected upward. An airfoil is shaped to cause an action on the air and forces air downward, which provides an equal reaction from the air, forcing the airfoil upward. If a wing is constructed in such form that it causes a lift force greater than the weight of the aircraft will fly. If all the lift required were obtained merely from the deflection of air by the lower surface of the wing, an aircraft would only need a flat wing like a kite. However, the balance of lift needed to support the aircraft comes from the flow of the air above the wing. Herein lies the key to flight. It is neither accurate nor useful to assign specific values to the percentage of lift generated by the upper surface of an airfoil versus that generated by the lower surface. These are not constant values and vary not only with the flight conditions but also with different wing designs. Different airfoils have different flight characteristics. Many thousands of airfoils have been tested in wind tunnels and in actual flight, but no one airfoil has been found that satisfies every flight requirement. The weight, speed, and purpose of each aircraft dictate the shape of its airfoil. The most efficient airfoil for producing the greatest lift is one that has a concave or a scooped out lower surface. As a fixed design, this type of airfoil sacrifices too much speed while producing lift and is not suitable for high-speed flight. Advancements in engineering have made it possible for today's high-speed jets to take advantage of the concave airfoil's high lift characteristics. Leading edge Kruger flaps and trailing edge Fowler flaps, when extended from the basic wing structure, literally change the airfoil shape into the classic concave form, thereby generating much greater lift during slow flight conditions. On the other hand, an airfoil that is perfectly streamlined and offers little wind resistance sometimes does not have enough lifting power to take the airplane off the ground. Thus, modern airplanes have airfoils that strike a medium between extremes in design. The shape varies according to the needs of the airplane for which it is designed. This figure illustrates the same, and it shows some of the most common airfoil sections. The different types of airfoils described here are an early airfoil, later airfoil, Clark Y airfoil that is subsonic, laminar flow airfoil that is also subsonic, circular airfoil that is supersonic, and double wedge airfoil that is also supersonic. Low pressure above. In a wind tunnel or in flight, an airfoil is simply a streamlined object inserted into a moving stream of air. If the airfoil profile were in the shape of a teardrop, the speed and the pressure changes of the air passing over the top and bottom would be the same on both sides. But if the teardrop shaped airfoil were cut in half lengthwise, a form resembling the basic airfoil wing section would result. If the airfoil were then inclined so the airflow strikes at an angle of attack AOA, the air moving over the upper surface would be forced to move faster than the air moving along the bottom of the airfoil. This increased velocity reduces the pressure above the airfoil. Applying Bernoulli's principle of pressure, the increase in the speed of the air across the top of an airfoil produces a drop in pressure. The lowered pressure is a component of total lift. The pressure difference between the upper and lower surface of a wing alone does not account for the total lift produced. The downward backflow from the top surface of an airfoil creates a downwash. This downwash meets the flow from the bottom of the airfoil at the trailing edge. Applying Newton's third law, the reaction of this downward-backward flow results in an upward-forward force on the airfoil. High pressure below. A certain amount of lift is generated by pressure conditions underneath the airfoil. Because of the manner in which air flows underneath the airfoil, a positive pressure results, particularly at high angles of attack. But there is another aspect to this airflow that must be considered. At a point close to the leading edge, the airflow is virtually stopped, that is stagnation point, and then gradually increases speed. At some point near the trailing edge, it again reaches a velocity equal to that on the upper surface. In conformance with Bernoulli's principle, where the airflow was slowed beneath the airfoil, a positive pressure upward was created. That is, as the fluid speed decreases, the pressure must increase. Since the pressure differential between the upper and the lower surface of the airfoil increases, total lift increases. Both Bernoulli's principle and Newton's laws are in operation whenever lift is being generated by an airfoil. Pressure distribution. From experiments conducted on wind tunnel models and on full-size airplanes, it has been determined that as air flows along the surface of a wing at different angles of attack, there are regions along the surface where the pressure is negative or less than atmospheric, and regions where the pressure is positive or greater than atmospheric. This negative pressure on the upper surface creates a relatively larger force on the wing that is caused by the positive pressure resulting from the air striking the lower wing surface. The figure shows the pressure distribution along an airfoil at three different angles of attack. The average of the pressure variation for any given angle of attack is referred to as the center of pressure, CP. Aerodynamic forces act through this CP or center of pressure. At high angles of attack, the CP moves forward, while at low angles of attack, the CP moves aft. In the design of wing structures, the CP travel is very important, since it affects the position of the air loads imposed on the wing structure in both low and high angle of attack conditions. An airplane's aerodynamic balance and controllability are governed by changes in the CP. Airfoil behavior. Although specific examples can be cited in which each of the principles predict and contribute to the formation of lift, lift is a complex subject. The production of lift is much more complex than a simple differential pressure between upper and lower airfoil surfaces. In fact, many lifting airfoils do not have an upper surface longer than the bottom, as in case of symmetrical airfoils. These are seen in high-speed aircraft having symmetrical wings or on symmetrical rotor blades for many helicopters whose upper and lower surfaces are identical. In both examples, the relationship of the airfoil with oncoming airstream angle is all that is different. A paper airplane, which is simply a flat plate, has a bottom and top exactly the same shape and length. Yet these airfoils do produce lift, and floor turning is partly or fully responsible for creating lift. As an airfoil moves through air, the airfoil is inclined against the airflow, producing a different flow caused by the airfoil's relationship to the oncoming air. Think of a hand being placed outside the car window at a high speed. If the hand is inclined in one direction or another, the hand will move upward or downward. This is caused by deflection, which in turn causes the air to turn about the object within the airstream. As a result of this change, the velocity about the object changes in both magnitude and direction, in turn resulting in a measurable velocity, force, and direction. A third dimension. To this point, the discussion has centered on the flow across the upper and lower surfaces of an airfoil, while most of the lift is produced by these two dimensions. A third dimension, the tip of the airfoil, also has an aerodynamic effect. The high pressure area on the bottom of an airfoil pushes around the tip to the low pressure area on the top. This action creates a rotating flow called a tip vortex. The vortex flows behind the airfoil, creating a downwash, and then extends back to the trailing edge of the airfoil. This downwash results in an overall reduction in lift for the affected portion of the airfoil. Manufacturers have developed different methods to counteract this action. Winglets can be added to the tip of an airfoil to reduce this flow. The winglets act as a dam, preventing the vortex from forming. Winglets can be on the top or the bottom of the airfoil. Another method of countering the flow is to taper the airfoil tip, reducing the pressure differential and smoothing the airflow around the tip. Chapter Summary. Modern general aviation aircraft have what may be considered high performance characteristics. Therefore, it is increasingly necessary that pilots appreciate and understand the principles upon which the art of flying is based. For additional information on the principles discussed in this chapter, visit the NASA Beginner's Guide to Aerodynamics. Thank you for watching, and like, share and subscribe for further videos. Thank you.